Welcome everyone. So, today we are going to discuss on RTL optimizations for area. So, in our last discussion we have discussed about several techniques which improves the timing of a design, or say throughput of a design, or the latency, improves the latency of a design. So, we discuss about certain strategies. Today discussion's topic is something on area. What are the kind of techniques that we can commonly used on RTL which actually improve the area. So, specifically we are going to discuss about strategies like folding, rolling of pipelining, resource sharing, and some reset, impact of reset specifically on FPGA targets. Okay. So, let us start with folding. So, what is folding transformations? So, whenever we design certain things, we do not keep in mind that similar kind of structures generate in many places, right, and they are all consume areas. It may be possible in certain scenarios that those kind of patterns can be clubbed together and can be used only one component, I mean one module of the same structure, which reduce the area by large. Okay. Let us take this example. Suppose I am doing here this multiply and add, multiply and in parallel. So, there are 4 such components in your design. I just copy paste from a different part of the design this has, and this also in if you just think about the hardware, I have 4 multiply and I have 4 adder, and these are all in running in parallel. So, what we can do, I identify this MAC pattern, right, multiply and accumulate pattern, and I just use only one of the pattern in your design, right, and now this input should be time multiplexed. So, this A input, the left input A, B, A, C, E and G will be clubbed together as a left input through a multiplexer, and the right input B, this B, D, F and G will be clubbed together as the right input of this multiplier, and then this x1, x2, x3 and x4 will be time multiplexed again to this adder, right, and this will be now controlled by this control signal, same control signal, say CS, and this is 2 bit, right. So, this is CS, and if it is 0 0, I am going to choose A B and x 1, right. So, that A plus B into x 1 is carried out, right. Then if it is 0 1, I am going to choose this C and D, here C, here D and here x 2. So, that C plus C in A into B into plus 1, here C into D plus x 2 is carried out. So, similarly 1 0 and 1 1, I am going to choose E and F x 3, and I am going to choose G, H and x 4, right. So, this is something in 4 clocks I am going to do this, right. So, we can understand that here your area will be reduced by multiple of 4, right. So, factor of 4, because I try to club 4 such patterns into 1, right. And now, if you can find out some k such pattern, your area will be reduced proportional to k times. Of course, there are certain things has to be taken care, because this multiplexer is adding, but usually this kind of pattern that we find out is a big pattern and consists of complex operations which we club together. So, the extra area overhead of this multiplier is kind of a negligible compared to the things that we are going to merge. Okay. So, this is overall folding structure. So, there are certain things. So, this is where I give an example where this 4 upper structure running in parallel, I just club together, but it is also possible to club operator that are in series. Okay, right. For example, I have these 2 adder in series, I can club them into one adder in the circuit. Then what you have to do? I have to use this A and B as the input here. So, this is A is the left input of this multiplier and B is the one input, and the C will be another input for this. So, I need a multiplier, and whatever the results here, that has to feed back to this adder, right. So, this is what I am doing. So, I just put a register here, and this output is feeding back, right. So, what happened? So, in first cycle this A 0 and B 0 will be calculated. In the second cycle, this A 0 is B 0 is already stored in these registers, and now this C 0 will be, so C 0 will be selected here, and then A 0 plus C 0 will be calculated. Again in the, so this is 1 bit signal, 0 and 1. So, 0 is just to select B and A, and the second cycle it will select this C x and this A 0 B 0, right. So, this is how the whole thing will work. So, every 2 cycle this whole this A 0 P 0 C 0, the output will come, right, in every 2 cycle. Okay. So, this is the both are possible. If they are in parallel, you can merge them. If they are in series, then also you can merge them, but you need a feedback register, so that you can reuse that intermediate results as well. Okay. So, this is the overall folding transformations, and so what are the other issues has to be considered here. So, the important factor is that here, so suppose this is the your folded structure, right, but this is not the only component of your design. So, this is just a part of your design and which is synchronized with the other part of the design. Okay. So, now earlier what is happening, since this all running in parallel or in series, there is no delay, in one clock you are going to get the results, right. So, now since this is taking multiple clock, then your this results whatever the input is coming here, you have to now wait for say 3 cycle 4 cycle to get the output, right. So, either you have to, if you want to run all this component in the same clock, then you have to add some synchronization mechanism, so that whatever the data is expecting after 1 clock, now it will wait for 4 clocks, because now your things are folding factor is 4. So, after 4 cycle only the data will be available. Similarly, this may be feeding data in every clock, now it has to wait for, hold the data for all 4 clock cycles, so that the operation can be executed here, right. So, there are two choices, either you add all the synchronization factor in your design, or the alternative choice is that you run this particular block, the folded block, n time faster, where my folding factor is n. So, that means n component is merged into a single block. So, now I can actually run this particular things in clock into n. So, if the clock is say here 10 and say folding factor n equal to say 5. So, this will be 50 megahertz and this is also 10 megahertz, right. So, what will happen? So, even though one clock of this is equivalent to the 5 clocks. So, effectively I am running in 5 clocks, but since this clock is very fast, it will be automatically synchronized with the other blocks, right. This is the common way of doing this. So, whenever you fold something, you increase that clock of that particular block by a factor of folding factor, which is n, so that your synchronization will be automatically taken care of, but the data will be seamlessly go through these components, right, because it is just for him this is 1 cycle, but effectively this is 5 cycle in internal. So, all these things will be properly synchronized. Okay. So, during folding these are the two things, either you have to synchronize manually or you just increase the clock speed of the folded structure, so that it can be automatically synchronized with the other component of your design. So, this is the two factor you have to take care of. Okay. And this folding transformation usually apply for this complex operations like multiplier, and it is basically time multiplex, right? The inputs are time multiplexed, and it is useful for DSP application, where actually you try to input maximum DSP in the sense DSP is a specific component in FPGA which actually can do multiplication very fast, and it also has some adder and accumulation option, pre-adder as well as accumulation option. So, you can actually find out a multiply and accumulate, or add and multiply then accumulate. This kind of structure you can figure out in your design, and you can actually use the same DSP to calculate that same thing. Okay. So, this is something is useful in DSP applications, and if you just think about the automating this step, you have to find out the first pattern, right, the common pattern. As big pattern you can find out, that is beneficial, because then the resource this area improvement will be by that factor. You try to, even if you find say one multiplier, so there is one multiplier for this design, you can just find out this multiplier 4 multiplier, and you can multiplex this 4 multiplier, right. But if you just find out multiply and, then actually you can replace all this 8 by 2, right. Earlier only 4 multiplier by 1 multiplier. So, you are actually saving is more. So, as big pattern you can figure out, that will be beneficial for your design, right. So, you have to first figure out the common patterns, then this folding factor depending on the number of patterns you have identified, then replace all this pattern by a single pattern with inputs are time multiplex. That means, you just add multiplexers and the control signal properly, and you apply a faster clock of n time faster clock to that folded circuit, so that the whole things work smoothly. Okay. So, this is all about this folding transformations. Now, we will move into the next topic, which is that pipelining. Pipelining also rolling up the pipelining is something we improve the area, right. So, this is the same example I discussed in one of the previous discussion, where we are talking about this improvement of the power, this improvement of the throughput. So, that x cube design, right. So, you can do it iteratively, or you can actually you can actually this apply, you can do it in a pipeline manner, that the way I just discussed in the in previous class, that you can do this all operations pipeline, so that your throughput is 8 bit per cycle, but you can roll this pipeline into one, which is that iterative version of this. So, I have only one multiplier now instead of 2 multiplier, and 3 register, I have now 1 multiplier into 2 1 register, right. So, if you just roll this pipeline, this is just the opposite operation. So, this is the iterative implementation and this is the pipeline implementations, and you can just if your area is concerned, then you should probably take this one, but this will take 3 cycle, right, because your latency will increase, because your throughput will be less, because now you are actually producing 8 bit in 3 cycles. So, it will be 8 by 3, and your latency also 3 cycle, because in every 3 cycle you are producing one output. In this pipeline design and this all this component running in parallel, we have shown that our latency is also 8 bit, and this throughput is 8 bit per clock, and your latency is 1, right. So, sorry, latency is 3 bit, but effectively your throughput is 8 bit per clock, right, because there are 3 latencies here, but your area is less here, because if you just do this iterative versions. Okay. So, this is what is called pipelining. So, if you have a pipeline design and really care about your area, your design is very big, and even saving this 2 multiplier is useful, you can probably do this implementation instead of this, right. But again, if you do this, you have some others synchronization like finish, because now it will take 3 cycles. So, you will generate some finish signal just to synchronize with the other components. Okay. So, this is something, it is your choice, it based on your, if your area is very crucial factor, then you are going to choose this, and if your throughput is important, then you are going to choose this one. Okay. So, there is another aspect is also here is sometime your design may be there is no pipeline, nothing, but there are some complex operation like multiplier, but you can think about as a alternative implementation of a multiplier, okay, which will actually give you better benefit, right. So, that is something also is possible. For example, if you just think about this, your implementation has only these multiplications A into B. So, you are effectively have a multiplication, which if you assume it is a big complex implementation. So, because it will be finally mapped to logic, right, and it will take lot of gates. But if you just think about, I am going to implement multiply by shift and add, right. So, then what is happening, you just shifting your multiplicand by every time, and you just add it based on the multiplier value, that is 0 or 1, right. So, if you just abstract diagram like this, so your every cycle you are going to shift this your A. So, you are doing A into B, right, this is A into B, and if your that particular bit is 1, then I am going to shift and I am going to add to the results that this is my partial results, multiplication results. So, otherwise I just discard this shifting value, right. This is very well known way of calculating multiplication using just a shift register and a adder instead of a multiplier, but it will take 8 clock, right, because every clock you are just shifting 1 bit and you calculate on these things. So, if you just assume ki my data path is 8 bit, then it will take 8 cycle, right. Every cycle I am shifting by 1 bit, and I am going to add, and then again I am shifting by another bit, and then I am going to add, and this will go for 8 cycle, and finally the result will be generated, right. But you can see that I can replace that big multiplier by a simple adder, right. So, it will give you a big area benefit, but again it is basically become a pipeline iterative version. So, it will take 8 cycle, but here the multiplier is going to take only 1 cycle. Okay. So, it is basically again I am just repeating the same statement, that is also design choice. If you are if you want to just achieve as low area as possible, probably, and your latency does not matter, because then probably you can replace this multiplier by a simpler version of multiply and add multiplier, which will take 8 cycle, right. So, your latency will become 8, whereas your latency here is 1. Okay. So, this is something also possible, and sometime you have to do this kind of optimization just to achieve your target area, because you maybe in your FPGA target your design is not get fit in, right. You need this kind of little bit changes in your design, so that the whole things get placed in your FPGA. Okay. Because in FPGA the number of DSP blocks are fixed, and the logic that LUTs and the logic units are fixed. So, if you have very large number of multiplier, you probably not able to fit all of them in the DSP blocks of the logic units, whereas you can just replace a multiply by add, and which will take less number of LUTs, and probably you can map it to the design. So, sometimes this kind of corner case might arise and you have to do this kind of tricks, so that you can actually map your design into a target FPGA devices. Okay. So, this is about the rolling up pipelining. I am going to talk about the next technique, which is called resource sharing. Resource sharing is something again it is kind of folding, but is in different manner. Is like if you have some resources is used many places, right. It is not folding into one, but some of the resource I can actually share. It is kind of folding, but it is little bit different in the sense that the structure may not be exactly same, but I can reuse that component. It is specifically applicable for counter. If we just take this example, suppose I have two module, here I have two counter, right, 11-bit counter and 8-bit counter. So, what I can do, I can just bring out this counter from this two module. I can have a dedicated counter module, which is 11-bit counter. I can use the 8 LSB as the counter of this, and the all 11-bit as the counter of this module, right. So, now I have a one counter module which is reused in the both the modules. So, I bring out this two counter out of this and we create a dedicated counter module and I can use this, right. So, this is what is called resource sharing. So, it is kind of finding out some similar type of module, I mean similar type of operations is happening in multiple hierarchical modules. You figure out, bring it out them and you do them once, and you just use that particular output in all the modules, right. So, that is what is called resource sharing. So, that is something sometime we usually do, because that is also give you a good idea. Because here I just give one example where counter is very common to your design, maybe there are say 100 counters and that is there in different module, and just doing this in 100 times is lot of area, right, but you can just do only once and I can use it for all the module. So, this is the kind of optimization that will give you very good area benefits. Okay. So, that is also an technique you should always remember when you are going to do this area optimization. Now, I am going to talk about several strategies specifically for FPGA target. Okay. So, this impact of reset on area for FPGA. Okay. So, as you remember or know that FPGA has very fixed kind of structure, right. It has set of CLBs. CLB is nothing but this configurable logic unit, which logic unit is consisted of the LUTs, which is that you can map any kind of combinational circuit into that lookup table based logic units. It has also some CLBs which consist of memories, which is basically register flip flops, and it also have some dedicated RAM ROM, this RAM memory unit like RAM ROM. It also have some shift registers, which is very fast and efficient way of implementing the shift registers, and also it has some DSP blocks, right. And the pin configurations, the problem with this, the pin configuration for this DSPs or say FPGA units are fixed, right. For example, a RAM may not have any say asynchronous reset, or say DSP block do not have any say synchronous set, or say shift register do not have any say reset pin, right. So, if you try to map your design to a FPGA, it is very important to understand the exact pin configuration of your design of the FPGA block, because what happens sometime is you design something without understanding the exact structure, and because of only a reset pin or say synchronous reset pin or say asynchronous reset pin, that particular whole big RAM or say DSP cannot be mapped to the target architecture, right. For example, you try to map a big array into some memory or say RAM, and because of that asynchronous reset it cannot be mapped to that RAM. Then there is a big problem, because then the whole RAM may be mapped to registers and it will consume lot of registers, and then your all the register may be overused. You cannot do other part of the register which should be mapped to register cannot be done, right. So, this is something the very small and very partial thing we are not always bothered about, but that actually create a catastrophic effect in your area, and it is just because of that particular unit, the DSP unit or the shift registers or the RAM does not support that particular kind of pin, and because of that it is not able to map that to the RAM or ROM, it is mapped to the logic units, logic flip flops or say CLBs or the LUTs, and it has a very bad impact on your area. So, we are going to discuss about this specific things, the pin configuration and what kind of impact might happen. in rest of this discussion. Okay. So, first we are going to discuss about the SIP register, and in the SIP register usually do not have any reset pin. SIP register usually do not have any reset pin, and then what happens if you just design a SIP register. Here I just talk about a reset. So, this is the SIP register, right. So, I am just shifting and I am just taking one bit again. Similarly, I am here this is just shifting and I am just taking a new bit. So, this is I am just shifting and just taking one bit at a time. But in this particular implementation 1, I have a reset. I just reset the whole SIP register, and there is no reset here. So, this reset is defined in this design, but in this particular I do not have any reset. So, this is a good design practice, right. We always make a reset, but it may be that in your design it does not matter the initial state. So, because you just plus out all your SIP register component and you just store your data and then you compute something, right. So, this is very common practice. It does not care about the initial data component, that will be it has no impact on your design. So, in that case when you may not define the reset, right. So, even if you just ignore the reset, you do not have any impact on your design. But the problem here is that since the resets the SIP register do not have any reset pin, there is no reset pin in the SIP register, this particular implementation cannot be mapped to the SIP register, dedicated register, the SIP register of your FPGA. Whereas, since this does not have any reset, this will be this can be mapped to the dedicated SIP register of the FPGA block, right. So, if you just do this, so what is happening, the implementation 1 is going to be mapping the normal flip flops which is in the CLBs, and that will be connected, right. So, it is a big chain of registers, whereas the implementation 2, because it does not have any reset pin, it can be mapped to the dedicated SIP register, right. So, if you just think about the resource implementation, I have only one flip flop here and one slice, because this is just for the implementation to just go into that dedicated SIP register, whereas this is actually mapped into multiple flip flops and slice. So, slice is basically in a CLB, what I just talked about in a FPGA, I have set of CLBs, right. So, these are all CLBs, and in CLBs configurable logic blocks, either I have LUTs or memories, right. So, so there are two types of units inside, either it has logic unit, which is basically memory slice. There are two type of slice, either memory slice or I have logic slice. So, memory slice nothing but the flip flops, and this logic slices has LUTs. Okay. So, now since I have to map it this whole 16 bit register into multiple, you need 9 slices and you need 16 flip flops to implement the SIP registers inside the CLBs, right. And in one CLB can have maximum 2 units, either 2 logic units or 1 memory unit, 1 logic unit or 2 memory unit, right. So, this is something inside the CLBs. So, you need 9 slices and 16 flip flops, because this is not mapped to SIP register, where it is just stored into 1. So, this is something you can understand that your area is getting when area will be worse for this if you have a reset, right. So, this is something sometimes we do not care about this, sometimes you need this, but most of the time I do not have the defined reset state, because it does not matter to your design. So, probably this is a better choice, because that will result in finding a SIP register instead of a mapping it to the normal registers of your design, of your FPGA. Okay. So, I will move into the next issue, like in DSP, resource without set. So, DSP unit of your FPGA does not have any set, it has reset, but it does not have any set. So, now you want to set some registers, right. For example, in this design what I just do the multiplication. So, my interest is to map it this multiplier to DSP, because DSP is very high speed multiplier. So, but it has a set, right. I am going to set some value to this register, right, under certain condition. So, this is synchronous set, right, because it is not this ID set is synchronous to this clock, because this is because this is not coming another which is not asynchronous to this clock, right. Even it is a synchronous set, but it is not, because I am setting this. So, this is not possible to map into this exact the whole these things into a single DSP, but if it is a reset, if I just write this O dat equal to 0 say, then this whole thing is going to map it into a single DSP, whereas because of this has to be carried out outside, right. So, you just give an example here. So, if you just do it here, so this is your DSP unit. Now, this setting up this setting up this value, you need some additional logic here, which is this. So, this logic is just setting up this multiplier results with this 1, right, all 16 1. So, this is something is the additional resource that you require just to have the set value, right. So, for example, here you just see that for the set example you need 9 slices, because this will going to map this 16 flip flop and this one DSP and one LUT, and for the reset one, because this all this thing whole thing I just reset means you just replace this by this id equal to 0, everything can be mapped into single multiplier, right. So, this is kind of you can understand that just do not having that set pin, and if you have to set it, you need extra resource to just execute that particular set operations in your design. Okay. So, this is one issue with the DSP with the set, and the second was like the asynchronous reset, right. So, again this DSP has synchronous reset, but it does not have any asynchronous reset. Okay. So, asynchronous reset means is that reset does not sync with your clock, it can come anytime. So, so this is then it will have a problem, right. So, this is something a generic DSP structure of an FPGA. Okay. So, we are discussing when DSP has reset signal and it does not have any set. So, it create a problem if you want to set it in the previous example, but again it does not have any asynchronous reset, right. Even if you have a reset in your design when which is not asynchronous, then that it will create a problem, right. So, here I give an example standard DSP unit. So, you can have a, you can see there is a multiplier, there is a pre-adder and there is a accumulator, right. So, there is a accumulator and there is a set of registers here, there is another set of registers here and there is a set of register here. You can see how many things you can just put into a single register. You can put a single multiplier into the DSP or multiply and accumulate in the DSP. You can put a pre-adder as well, right. So, you can just do A plus B. So, here this is basically A plus D into B, right. You can do this also, and then you can just accumulate. It says basically x equal to x plus this. You can do the whole thing in the same multiplier, and also not only that, in this design you can have 3 set of register as well. So, you can put this so that this delay become less, right. So, you can actually put set of register also. So, you can understand how many, what is the function, I mean what are the different variations of multiplication, I mean operations can be performed by a single DSP, and it is your choice. You have all this configuration, you can choose either only multiplier, multiply and add, pre-adders, so this one set of register, 2 set of register, 3 set of register. So, all these things can be done, right. But and it is very efficient and very fast dedicated unit, right. But if you have a asynchronous reset in your design, then it will create a problem, right. For example, in this multiply I am to do this multiply and add, this is MAC multiply and then you just add it, right. That is what I am doing here, but I have a asynchronous reset, right. So, this is passage of clock or negative edge of I reset. So, this is asynchronous, right. So, then I am just reset because I am just resetting the multiplication factor and the output. But the problem is that since this is asynchronous reset, this cannot be the whole structure, because this cannot be just, this reset pin cannot be just connect to the reset pin of this. So, there may be a reset pin here, it cannot be connect to the reset pin of that particular MAC, because this is asynchronous. So, what will happen, this particular extra thing has to be implemented outside of the DSP block. So, this can be mapped to DSP, but this has to be go to outside of the DSP block. And if you just see here, so and that will actually create a problem, right, because this is your DSP. So, this is the multiplier will go to the DSP. So, DSP and then there are some logic, right, just to logic to async reset. So, this has to be there, so that you can do this asynchronously. So, and this will create extra area, right, that will need extra area. If you just the results are here. So, if you just do the synchronous reset, that means this is not there, then I need only one DSP. So, all these reset everything will be mapped to the same DSP, but if you have this asynchronous reset, then I have to, this extra logic has to map into this LUTs. I need 16 flip flops, because now these are some set of register required. I need 17 slice and 16 LUTs, and I need the DSP just to do the multiplication. This is the extra resource I need just to do this asynchronous reset. So, these are the kind of things that actually have an impact on area, and we should actually aware of whether if this may not be absolutely necessary to make it asynchronous, right. So, then probably you can remove this. So, you should aware of that particular kind of issues when you are actually mapping these things to FPGA. Okay. So, now we are going to talk about the RAM. So, we have discussed about shift register, we have discussed about DSPs, now we are going to discuss the pin configuration of RAM. So, RAM has synchronous reset, it does not have any asynchronous reset or asynchronous set. Okay. So, if you use any asynchronous reset for your design, and it has a bad impact, catastrophic impact on your optimization, because then the whole, because array RAM is a big unit, right, and you cannot map the whole thing. If you do not map that particular thing into RAM, those will be mapped to registers, and this is a disaster, right, because that will consume lot of register of your design. So, in general, resetting a RAM is a poor design practice, right. You should not usually do not reset a RAM. So, that is actually have a very bad impact on FPGA design, specifically if your reset is asynchronous. Okay, because in that case that RAM will map to the huge number of registers. Okay. So, you just take an example here. So, in this particular RAM I have a asynchronous reset, right. So, this is not, and I am just resetting the resetting that register when this RAM, right. So, if it is asynchronous reset, then the problem is that the whole thing cannot be mapped, this particular memory, the big memory cannot be mapped to the RAM, and what will happen here, this will map to the normal registers, and you can see the difference. If I have a synchronous, I do not have this asynchronous reset, then I can probably infer just single RAM for the whole design, because this is nothing but a memory, just I am adding a memory operation, I just storing some memory, reading memory and writing memory, right. So, so I have just inferred a VRAM. Okay. Whereas, if it is a asynchronous reset, I cannot infer a VRAM and everything map it to LUTs, right, the memory, the slices and CLBs, and you can see the kind of impact of this, right. I have just a RAM which is mapped there and it is taking thousands of slices. Okay. So, this is something is very have a bad impact. So, when you are designing something for FPGA, we should avoid resetting a RAM. Okay. So, that will have a impact, specifically if it is specifically asynchronous reset. Okay. So, here is that extra logic is showing just to do the asynchronous reset part. So, this is that small RAM, and this is the asynchronous reset part which actually resetting that particular output. Okay. So, this is something is a give you a very fair idea how that asynchronous reset impact in VRAM inference. Okay. So, now we are going to talk about this the last component of this. So, even in the flip flops, the registers have the set and reset pin, and utilizing them actually have a area benefit, right. So, we try to utilize, those particular set and reset whenever possible, because that actually give you give area benefits, and if it give you area improvements, right. For example, in this particular design, so I have this some combination logic, and there is a OR gate here, and then I have a signal. So, OR with this, right. So, if this signal is 1, then this definitely is 1, right, and it does not matter what is computing here. So, what I can do, I can just make this as the set signal, right. So, I just remove this OR gate from my design, and I just put this as a set, because once this is this, the register will definitely become 1, right. It does not matter what is coming from other part. So, I can just set the register based on the signal A. So, it actually reduce the 1 OR gate, what we just talked about here, right. So, you just remove 1 OR gate. So, your area will benefit by 1 OR gate, and your computational delay will also improve by 1. Similarly, if you AND gate, I can actually infer a reset pin out of it, right. So, for example, here again the same example, but I have AND gate here. So, if this is 0, this will become 0, right, the output will become 0, because this is a resetting that thing, right, it does not matter what is this. So, what I can do is I remove this AND gate, I can put this signal as the reset pin, to the reset pin, negation of reset pin, right. So, if it is if the input is 1, then it is definitely 0, otherwise it will just consider. So, if it is 0, then it is become 1 and this is reset, and if it is 0, sorry, if this is 1, then this will become 0, it will not reset the pin. So, now it will, the input will depend on the combinational logic. Again, if you just try to utilize this, you actually have a area benefit, you can actually improve your design, you can remove 1 AND gate from your design, and again it will give you some timing benefit as well. So, overall the idea is that using the set and reset pin can prevent certain combinational like optimization. So, we should always try to keep this option open, so that I can actually, and this actually primarily done by the synthesis tool, right. So, if you do not use that set and reset pin unnecessary from your design, and if you have this kind of things, the tool will automatically map those AND and OR gate to the at the set and reset pin. So, you do not have to do anything, but you have to keep in mind that if you just unnecessarily using your set and reset pen, this will not be done by the synthesis tool, and then it will just unnecessary and one AND gate or gate in your design. So, the idea is that when you are designing something, you should always try to keep your set and reset pin unused, so that this kind of combinational optimization can be done by the synthesis tool, specifically for FPGA target. Okay. So, so we will just conclude with this. So, what we have discussed today, we have discussed several strategies that actually have an impact on area of your in your design. We have discussed about this folding, how folding can improve your area. We have designed this pipelining, rolling up pipelining, so that you just make it iterative, so that you can actually have a good area benefits. We also discuss about certain resource sharing, specifically for counter, how can I share the same counter for multiple designs even if they are not the same exactly same counter. And also we have discussed several strategies that how to use that reset and set pin of this FPGA devices, different component of FPGA devices, so that you can actually map better way in the FPGA. Right. Specifically, we have discussed about this shift register. You should not use reset for shift register. You should not use asynchronous reset or synchronous set for DSPs, or as a whole you should not have use reset for RAM. Specifically, you should not use asynchronous reset for RAM, because those have a very catastrophic effect in area performance. Also, we have discussed about that usually for flip flops you should keep the reset and set pin open, so that synthesis tool can actually map certain logic as a reset or set of this, which actually have a better area benefits. Okay. So, in the next class we are going to discuss about this optimization technique for power, how to improve power using some RTL optimization technique. Okay. Thank you.